All right, guys, Mr. Antonucci here, and this is our third and final part of our mid-year review for calculus. So let's jump right in. The function f given by f of x equals what we have here has a relative max at x equals what? Okay, to get a relative max, you have to look for a sign change from positive to negative in the derivative. So first thing we'll do is go ahead and differentiate. So we have 15x to the fourth minus 12x squared minus 3, set that equal to 0. Now, I'm going to factor out a 3 to reduce this a little bit. So you have 5x to the fourth minus 4x squared minus 1 equals 0. Now, you could use quadratic formula, but this is going to factor pretty simply. So we're looking for two factors here. Since 5 is prime, I know one's going to be 5x squared and the other one's going to be x squared. So you have to multiply to 5x to the fourth. Also, the lasts have to multiply to -1. So you're going to have a 1 times another 1. One of them is going to be positive. One of them is going to be negative. If I make this one negative, when I FOIL it, I'd get negative 5x squared. And then this one's going to give me a plus 1x squared, which gives me the -4. So this is equal to 0 only when this factor is equal to 0. And that's going to occur when x equals plus or minus 1. Okay, this factor is never equal to 0 because it's a sum of squares. So then we can make our sign chart -1 and 1, pick values before, between, and after those numbers and test the sign of the first derivative. If I plug -2, I always like to plug it into the factored form because then it easily multiplies. If I plug -2 in, you have 3 times a factor that's going to be positive times a factor that's going to be positive as well. So this is positive here. So f prime is positive, meaning f is increasing. When you plug in 0, you have 3 times a positive times a negative, which is going to result in a negative. So I know x equals 1 going to be a -1 is going to be a relative max. And then if you plug in 2, you would have 3 times a positive, which is going to be a positive. So +1 would be a relative min. So x equals -1 would be our relative max there. Okay. So the line normal to the curve y equals root here at the point 0.04 has slope. So normal is perpendicular to the tangent line. So this is as simple as taking the derivative, evaluating it at 0, and taking the opposite reciprocal of that value. So y prime is equal to, now remember the square root trick, it's the derivative of the inside over twice the original square root. I've taught you this before. So we're just going to go with that there. So dy dx is equal to -1 over 2 root 16 minus x. So if I do dy dx evaluated at x equals 0, I get -1 over 2 root 16, which is -1 over 2 times 4, which is 8. Now, that is the slope of the tangent line. The normal line, you're going to take the reciprocal and change the sign, so you would have +8, which is choice A here. All right, number 3. So if y equals this implicitly defined equation here, when x equals 1, dy dx is, so first we got to start by taking the derivative. I'm going to use y primes instead of dy dx. So y prime equals product rule here for the xy. So derivative of the first is 1 times second is y plus first times the derivative of the second. Now, the derivative of x squared, 2x, and the derivative of 1 is 0. Now we have to solve for y prime. So collect your y prime terms on one side. So subtract the xy prime to the other side. And then you'd have y plus 2x. Factor out a y prime. You'd have 1 minus x equals y plus 2x. So y prime equals y plus 2x over 1 minus x. Now you notice they told you that x equals -1, but you have a y in our equation here for the slope or for the derivative. So we could plug -1 back into the original function or equation rather and solve for y. Hopefully that'll work. And it will in this case. So y equals negative x or xy, so -1 times y plus -1 squared is going to be 1 plus 1. So if I solve this for y, I would have 2y equals 2, so y equals 1. So if y is 1, you'd have 1 minus 2, where x is -1, over 2. So you have -1/2, which is that choice right there. All right. Number 4, the triangle shown above, if theta increases at a constant rate of 3 radians per minute, already I'm thinking a related rates problem. Okay. At what rate is x increasing in units per minute when x equals 3 units? So right here, they told us d theta dt is 3. The moment that they're talking about is when x equals 3. Now, we're not going to plug that 3 in until after we differentiate. So we want to set up an equation that relates the quantities involved. I have an angle, the opposite, and the hypotenuse of a triangle. So I'm going to use sine theta, which is equal to x over 5. Now I'm going to differentiate both sides with respect to t. So this would be cosine theta times d theta dt. Remember, implicitly defined function of t. X over 5, the derivative would be 1/5 times dx dt. It wants to know what rate is x increasing, so we're solving for dx dt. So just multiply by 5. So it's 5 cosine theta d theta dt. Now, we know d theta dt because they gave it to us. It's 3. But we don't know cosine. Now, from the triangle, cosine is adjacent over hypotenuse. So if x equals 3, then a is going to be the square root of 5 squared minus 3 squared, which is square root of 25 minus 16, or 9, which gives us 3. So 25 minus 9 is 16, which gives us 4, square root of 4. So a is 4. That's that side. And then cosine is going to be adjacent over hypotenuse. So we have 5 times 4 over 5 times 3, which is going to be 12, which is choice E for that one. Okay. All right, number 5 through 7, we're going to use the information in this graph. So we have a function f defined on a closed interval 0 to 8. The graph of its derivative f prime is shown here. So be careful. The graph is for f prime. So we have to look at questions 5 through 7. What are they asking us about? So the point 35 is on the graph of y equals f of x. So they're giving you a point, an equation of the line tangent to the graph of f at 3, 5 is. So now we need the slope, which is equivalent to the derivative evaluated at 3, which from the graph, the value of the derivative is 2, not 0. I know there's a horizontal tangent, but the graph you're looking at already is the derivative. So our equation of the tangent line is going to be y minus the y value, 5, equals 2 times x minus the x value, 3. All right, so that's going to be choice C there for that one. Now, number 6, how many points of inflection does f have? So points of inflection occur when the second derivative goes from plus to minus or minus to plus. Okay, but on the first derivative, it would turn out to be relative extrema. Okay, because think about it, the second derivative is the slope of the first derivative, and if the second derivative is changing sign, then the first derivative's slope is going to be changing sign. So if we look here, we have 1 2, 3, 4, 5, 6 relative extrema, and that's choice E. Number 7, at what value does x does the absolute minimum of f occur? Now, a subtle but important point is that f is defined on a closed interval, so you have to look at the critical numbers and the endpoints. So we have an endpoint at 1, we have an endpoint at 8. And now, since this is the derivative, the critical numbers for f are going to be where the derivative is 0 or undefined, namely at 4 and 6, and the derivative here is never undefined. Okay, at 4, the derivative does not change sign, and at 6, the derivative changes sign from positive to negative, indicating a relative max. None of those are mins. So look at what's happening though. The endpoints, we have to check those. At this endpoint, the derivative is positive all the way until you get to 6, which means f is increasing from 0 to 6, and then from 6 to 8, the derivative is negative, which means it's decreasing. But the amount that it had to increase from 0 to 6 is way more than the amount it had to decrease from 6 to 8. So the absolute min is going to occur at x equals 0. Okay. Now, moving on to number 8, the graph of f prime, the derivative of f is shown. So again, be careful. We have the derivative graph. Which of the following describes all relative extrema of f on the interval? So critical numbers occur when the derivative is 0 or undefined. So that would be here, here, and here. Since the options are talking about relative max and mins and distinguishing, we know a max occurs when the derivative changes from positive to negative. So that would be right here. And a min occurs when the derivative changes from negative to positive. So that would be here and here. So you have one relative max and two relative mins. Choice A. And what are all x values for which the function f, defined by f of x here, is increasing? So f is increasing when the derivative is positive. So we got first take the derivative. You get 3x squared plus 6x minus 9. Set that equal to 0. First factor it, so factor out of 3. X squared plus 6x minus 9 equals 0. No, this would end up being, if I factor out of 3, this would end up being a 3, and this would end up being a 2. Sorry about that. So you have 3 times x plus 3 times x minus 1. Set that equal to 0. And then this factor would give you x equals negative 3, and this one would give you x equals 1. So we could set up our sign chart, negative 3 here, 1 here, and then I'm going to pick a value before, between, and after each critical number. So I'm going to pick negative 4, 0, and 2. When I pick negative 4, the signs of the derivative, I'm going to use the factored form. You would have the 3 out front times, if I plug in negative 4, that first factor is going to be negative. The second factor is going to be negative, which ends up giving me a positive, so I know it's increasing here. The next interval, when x is 0, I'm going to have 3 times a positive times a negative, which results in a negative. So the derivative is negative from negative 3 to 1. So that means f is going to be decreasing. And then when I plug in 2, I would get 3 times a positive, which is a positive. So f is increasing there. So I know f is going to be increasing when x is less than negative 3 or x is greater than 1, which is choice C here. All right, moving on to the next one. All right, guys, number 10 here, we want to find the slope of the line tangent to this implicitly defined curve at 2, negative 1. So let's go ahead and differentiate implicitly. So the derivative here is 2y, y prime, plus, now we got to do the chain rule here. So it's 3 times the stuff squared, the stuff's still there, times the derivative of the inside. Now this inside is the product xy plus 1. The derivative of xy is going to be derivative of the first, which is 1, times the second plus the first times the derivative of the second, and then plus the derivative of 1, which is 0. So you just close your parentheses there, equals 0. Now, I recommend, this is going to simplify your life a whole lot. If you just evaluate the derivative here by plugging in the x and y, and then solve for y prime. It's going to get real messy trying to solve for y prime here before you plug in the numbers, okay? So we're going to plug -1 in for the y's, and 2 for the x's. So this is going to be -2y prime plus 3 times xy would be -2 plus 1 squared times y, which is -1 plus 2y prime equals 0. So this is -2y prime. -2 plus 1 is -1, but you square it, you get 1 times 3 gives you plus 3 times -1 plus 2y prime equals 0. Got to distribute that 3, so -2y prime minus 3 plus 6y prime equals 0. If we combine the y primes, you get 4y prime, and bring the 3 to the other side, you get 4y prime equals 3. So y prime equals 3/4, or choice D. Okay? Now, moving along, number 11. If f and g are twice differentiable functions and h equals f of g, then h double prime equals, well, you got to find the second derivative, you got to find the first derivative. So h prime, this is a chain rule because it's f of g of x, not f times g of x. So it's the derivative of the outside at the inside times the derivative of the inside, g prime. The second derivative, we got to do a product rule and a chain rule because you have the f prime of g times the g prime. So here we go. Derivative of the first piece right here, f prime of g, is going to be f double prime of g times g prime. So that's all of that so far is just the derivative of the first times the second, g prime of x, plus the first, f prime of g of x, times the derivative of the second, which is g double prime of x. Okay? Now, you have a g prime times a g prime, so this is going to simplify a little bit to f double prime of g times g prime of x squared plus f prime of g of x times g double prime of x. Okay, so that looks a lot like choice A to me, and that is the answer there. All right. So now moving on to number 12, the graph of y equals h is shown. Notice this is the original function. Which of the following could be the graph of h prime? A couple things I would like to look for. I'd like to look for where the change in concavity is. If I can identify it, that's essentially at x equals 0. And for the relative extrema, one, you have a relative max before the origin and a relative min after the origin. So I know f prime has to go positive, negative, positive. In the second derivative, well, the graph looks like it's concave down, and then it switches to concave up. So I'm looking for a graph where the graph goes positive values, negative values, positive values. So A is not going to be it. B is not going to be it. C is not going to be it because it goes negative, positive, negative, and I want positive, negative, positive. D and E are the ones that go positive, negative, positive. But which one is going to result with a point of inflection at x equals 0? It's going to be graph E because points of inflection show up as relative extrema on the derivative. Also, the derivative is decreasing before 0 and increasing after, which means the second derivative would be negative before the origin and positive after. So that's choice E for that one. Number 13, let f be a function defined and continuous on the closed interval a to b. If f has a relative max at c, and c is between a and b, which of the following statements must be true? Okay? F prime of c exists. Not necessarily. Even though the function is continuous, it doesn't say that it's derivative, it's differentiable on the whole interval. So you could have a situation where, like from A to B, you have an absolute value function with the vertex right here at C. This function is continuous, defined on the interval A to B, but the derivative would be undefined at C. So f prime of C does not have to exist, so this statement doesn't have to be true. Now look at number two. It says if f prime of C exists, then f prime of C equals zero. Well, yeah, at a relative max, if the derivative exists at a relative max, it's a critical number, and critical numbers are either zero or undefined. If it's not undefined, then it has to be zero. Okay. And then if the second derivative has to exist and you're at a relative max, the graph must be concave down at that point, meaning the second derivative has to be less than or equal to zero. Okay, so it's choices 2 and 3 only. So that would be choice E for this one. Okay. Number 14, let f be continuous function on the closed interval, -3 to 6. If f of -3 equals -1 and f of 6 equals 3, then the intermediate value theorem guarantees that, okay, so the intermediate value theorem is an existence theorem, and it's saying that essentially if a function is continuous on a closed interval and it starts at one y value and ends at the other y value, it has to pass through all the other y values at least once. So if we're at -3, -1, and then 6 comma 3, if the function's continuous, then somehow it has to pass through all the y values. Well, be careful with how I draw that. Um, it has to pass through all the y values. I don't know if it goes above or below them. I don't know how many times it hits them, but it has to hit every y value between -1 and 3. It has to hit them at least once between the x values of -3 and -6. So f of 0 equals 0, that could be true, but that's not part of the intermediate value theorem. F prime of C equals 4/9, that would be the mean value theorem, and that doesn't necessarily apply because the function's not, doesn't say that it's differentiable. So f has to be between -1 and 3, between -3 and 6. That's not necessarily true because the y values could go above or below, but you don't know. For D, f of C equals 1 for at least one C value between -3 and 6. This is the answer because it's basically saying the y value has to pass through 1 at some point on the interval if the y values go from -1 to 3 and the function's continuous. Okay, this one just has the wrong values in there. So choice D on this one. All right, we made it to the last one. If dy dx equals √1 minus y squared, then the second derivative is, all right, so the second derivative here, we can apply the square root trick that I taught you earlier. The derivative of a square root is the derivative of the inside over twice the original square root. Now the derivative of the inside is going to be -2y prime. Now that's none of the choices there, but if you look, we know what y prime is. It's square root 1 minus y squared. So I'll just plug that in. The 2's are going to cancel first off. So you have -y square root 1 minus y squared over square root 1 minus y squared. Notice the roots are going to cancel and you have -y, which would be choice B for that one. All right, guys, that wraps up midterm review number 3. Hope that was helpful to you. Reach out if you have any questions, and take care.